Okay, previously we had looked at the following problem. We're going to revisit it. Okay, if F is the vector field with components x, y, and then z, and then 3z, and capital S is the union of the 6 rectangles that form the boundary of the box 0 to 6, Cartesian product 0 to 5, Cartesian product z values go between 0 and 4, then we had previously computed that the integral over the surface of f d bold s, or if we write it as f dot and then vector n, d just capital plain S, this was 660. So we computed the flux previously. Maybe go look for this. I believe this was 3 class days ago. Okay. Now, just I'd like to recall here briefly the horror involved in making this computation. We actually had to parameterize 6 separate surfaces, and then we set up 6 integrals. Now, none of the individual integrals were all that bad. Neither were any of the parameterizations. I think the pain of this was just that there were 6 of them separately to set up, right? Because we were talking about a box, yeah, and there was parameterizing the top, parameterizing the bottom, orient up, orient down. There was parameterizing the rectangle on the left and the rectangle on the right, parameterize leftward, parameterize rightward. There was the square in the back, and there was a square in the front, and parameterize rearly and forwardly, or whatever, right? And all of that, go look for it. Go look for the work that was involved. Go look for that number 660. Now the point is, we're going to revisit the same question. Let's now, with all the same setup, compute the flux again. The flux of this vector field across the surface. This is a closed surface because it's the boundary of a box. By closed surface, we mean like if you had the surface, the word closed, S is a closed surface. Sorry, I should have mentioned that in the last part. It means that the surface itself ends up trapping a 3-dimensional region. So it's like, how do we say this? The surface is like it's like the peel of a pillow. How do we say it? Like if you have the surface S and it truly is closed, it means that there's air trapped inside the surface, and then there's the rest of the world outside the surface. And the air that's trapped on the inside, if we don't think of it as air, but think of it as being made out of something else, like Play-Doh, would be the trapped 3-dimensional region. Okay, cool. So then, to do this by the divergence theorem, this integral there is equal to the triple integral over capital E of the divergence of the vector field dv. dv, by the way, right, meaning as kind of usual from the previous chapter, like dx times dy times dz, or you can switch up the order. And by E, we actually mean E is the box itself here. So the box here, or described like this, that's capital E itself. Right? So let's actually write that down over here. That capital E is really the set of all points where the x-coordinate is between 0 and 6, the y-coordinate is between 0 and 5, and the z-coordinate is between 0 and 4. So the actual filled-in solid box is the capital E, is the 3-dimensional region E. The divergence of F, well, F is up here. The divergence is, remember, is a scalar. The divergence of F, let's write it a little bit because it's first time, right? So it's this dot F. So take this should be a scalar. Dot product should result in a scalar. So we're going to add three things together. In fact, we take the first component, differentiate with respect to x, and we get a y. Take the second component, differentiate with respect to y, and you get a 0. Take the third component, differentiate with respect to z, and you get a 3. So we get y plus 0 plus 3. In other words, we get y plus 3. So then, the whole point is that we're using the divergence theorem. So instead of computing the integral directly, which was 6 separate surface integrals, we did that 3 class days ago. We're going to instead do this integral. So just as a new way to compute the integral, this flux integral, instead of computing what we were asked. Oh, sorry, I'm already like writing it differently. But same deal, yeah. We're gonna, so due to the new divergence theorem, we're going to compute the triple integral over the region E of the divergence of f dv, and this works out super nice, okay? Because let's write this as an iterated integral. So divergence of f is y plus 3, and then let's just go ahead and do this as a dx, dy, dz. X we see goes from, 0 to 6, y from 0 to 5, z from 0 to 4. And this is really, really not bad. Look, the point is the integrand here doesn't even mention x at all or z at all. So let's just take that shortcut. The x integration 0 to 4, so times 4. The z integration. No, sorry. Let's try that again. The x integration was the inside one. Apologies. It's from 0 to 6. Okay. The z integration is from 0 to 4. But then we're left with 6 times 4 times integral from 0 to 5 of y plus 3 dy. I mean, literally, this is it. It's going to be 24 times, and then what? Y squared over 2 plus 3y evaluated at 0 and at 5. Plugging in y as 0 is going to just turn that into 0. So we really just have 24 times 5 squared over 2 plus 3 times 5. And due to how this distributes and all that, let's not work out the arithmetic. You just put that in a calculator. You're going to get the number 660 again, which is going to match the number we got earlier. The point was, when we did this before, it was super tedious, and now this new way, using the divergence theorem, this is much nicer. I mean, we actually really technically finished this all the way through, and it was very nice.